Hey, welcome. Today, we're going to dive into the invisible technology that basically runs our world, sensors. They're the unsung heroes, the digital nervous system that connects our physical reality to the world of data. We're going to decode how they work, from the rigid silicon inside our phones all the way to the soft skin on our bodies.
I mean, just think about it for a second. That little buzz you feel on your phone when you press a button, that's a sensor. And the crazy, complex safety systems in your car that know exactly when to brake, oh yeah, they're absolutely packed with sensors. They're the critical bridge between what we do in the real world and the digital responses that are just a part of modern life.
Look, we've gotten really good at building sensors for hard, predictable machines. But there's a much bigger challenge on the horizon. How in the world do we create sensors that can work with something as soft, as dynamic, and as complicated as our own biology? That right there, that's the core question we're going to tackle today.
So to really understand what makes a real-world sensor tick, and, what makes it fail, we first have to imagine a perfect one. What would an ideal sensor, a flawless translator of physical information, even look like in theory?
Okay, so at the heart of every single sensor is this thing called a transfer function. The best way to think of it is as the sensor's main rulebook. In a perfect world, it's this beautifully simple one-to-one translation. You give it a stimulus, say some pressure, and it gives you a perfectly precise, totally predictable electrical signal in return, every single time, just like a flawless interpreter.
In this perfect sensor, it has two key superpowers. First, it's time invariant. That just means it works exactly the same on day 100 as it did on day 1. Its performance never ever degrades. Second, it's monotonic. So if you keep increasing the input, the output only ever increases. It never gets confused or goes backwards. But, of course, reality is never that simple, is it?
All right, so let's get real. The first set of problems engineers run into are called static characteristics. These are the built-in flaws that have nothing to do with time, but they have everything to do with the sensor's basic design and the materials it's made from.
Now, this slide right here clears up a classic point of confusion, the difference between accuracy and precision. So imagine you're shooting arrows at a target. Accuracy is how close you get to the bullseye. That's the true value. Precision, on the other hand, is how tightly all your arrows are grouped together, even if that group is way off in the corner. An ideal sensor has both, but a lot of real ones struggle with one or the other.
Then you've got this fascinating flaw called hysteresis. It's almost like the sensor has a memory of where it's just been. The reading you get for a certain amount of pressure might be different depending on whether you're increasing the pressure to get there or decreasing it. This lag creates this frustrating zone of uncertainty that's a real headache to deal with.
And the list of these little glitches goes on. Nonlinearity just means the sensor's response isn't that perfect straight line we dreamed of. Saturation is basically when you hit a ceiling. You can keep cranking up the input, but the output just flatlines. And the limit of detection? Well, that's the quietest whisper the sensor can actually pick up.
Okay, so on top of all those static flaws, there's a whole other category of problems, the dynamic flaws. This is all about how sensors behave when they're racing against the clock, trying to respond to changes happening over time.
So how fast is fast enough? Engineers have a few key metrics for this. Think about the airbag sensor in your car. It needs an unbelievably fast response time to work in milliseconds. Things like rise time, the time constant, and bandwidth help engineers put a number on that speed, telling them the full range of signals, from really slow changes to super fast vibrations, that the sensor can actually track.
To get a handle on this behavior, engineers think in terms of orders. A zero-order system? That's the impossible dream, like flipping a light switch and getting light instantly, no lag. A first-order system is more realistic. Think of a thermostat that takes a moment to catch up to the room's temperature. But a lot of physical sensors are second-order. They can overshoot the real value and then oscillate, kind of like a bouncy spring, before finally settling on the right answer.
Now this slide, this is where things get really cool. It shows this beautiful analogy. The physics that governs mechanical systems is a direct mirror of electrical systems. The inertia of a mass acts just like an electrical inductor. The energy storage in a spring is just like a capacitor. And the energy loss from a damper, like a shock absorber, is pretty much the same as an electrical resistor. It's the same physics, just speaking a different language.
So, what's the big takeaway from all this? All of these performance characteristics, the static ones, the dynamic ones, they aren't just abstract ideas. They are the direct result of the physical materials used to build the sensor. And this brings us right back to our main challenge. Here it is, the core of the problem. Our most advanced electronics are built from hard, rigid silicon. Our bodies are soft, flexible, and very much alive. When you try to stick the two together, you get this massive mechanical mismatch. And that can lead to everything from simple discomfort to actual tissue damage, inflammation, and even the body's own immune system attacking the sensor like it's a foreign invader.
And look, this isn't just some academic puzzle. For everything from next-gen prosthetics to real-time health monitors, bridging this gap between hard electronics and soft human tissue is an absolutely urgent, critical need for medicine and engineering today.
So how do we fix this fundamental mismatch? Well, the solution is pointing us toward a future where the lines between us and our machines might finally and safely start to blur. The solutions are coming from some incredible innovations in material science. We're talking about making components so small they're microscopic. That's a field called MEMS. We can build metal interconnects that are shaped like tiny springs so they can actually stretch. We can use soft gels and polymers, like PDMS, to wrap around the rigid electronics like a cushion. And we're even developing brand new organic semiconductors that are just naturally flexible, right down to the molecular level.
This whole wave of innovation is paving the way for a future of seamless biointegration that could totally revolutionize medicine. But it also raises a much bigger, more profound question we all need to think about. As these sensors become less like tools we use and more like a part of who we are, what will it truly mean to be human?